So it's opening up Explorer.
Yeah, it's because Zoom insists on using Explorer for some bizarre reason.
Okay.
But now if you go back to Firefox,
And
looks like here. Can I see? It might just be because we don't have any video on the Zoom meeting at this point in time.
yeah, why not? I thought I clicked that. There we go.
Okay. So there's a bit of delay, so I'll let you know if it updates or not. There it goes. So yeah, we're good. So yeah, we're streaming. I'll edit the title of the stream because it's a bit out of date.
Start off with Blackboard stuff.
Okay.
And do you have a pile of chalk something, or is it all?
That other box might have larger pieces. I don't believe it's in use yet.
Do you have your phone?
Yeah. You know. Got the water hot, but give me like 5 minutes before you do this demo here so I can get it boiling again.
Okay. Your phone?
Yes.
Yeah, probably when we do the convection box.
Okay.
Because that'll be the first convection demo I do, and that'll do.
Just hit that. Okay. So I'll light the candle in the convection box and then I'll get that moving again. Anyway. There you go. Where's the hot mic?
Okay, folks, it's about time to get started. Oh, a couple of things that, looking back through the book and thinking about what's important, I neglected to talk about. We were talking about motion of fluid. Wow. And something that's pretty important for understanding the Bernoulli effect, the idea that pressure is low in any fluid where the fluid velocity is high, and the pressure is high where the fluid velocity is low. It's the continuity of a fluid. If a fluid is not squishable or compressible, which water tends not to be, when a lot of fluids, other fluids we tend to deal with are kind of that way. If the fluid is not compressible, we can say that pretty much we have the same flow rate, number of gallons per minute, or liters per minute, or liters per second, or basically the cross-sectional area of fluid times its speed. And I'm using the Van Halen V here for speed because the book uses V for both volume and for velocity. So just to make it clear that I'm talking about velocity, I'm using a Van Halen V, which always looks faster than just a regular V. Okay. So basically, you look at that, you've got like square meters times meters per second. So the units are basically cubic meters per second, basically volume of fluid per second. This tends to be fairly constant. And for those of you who like to fish on rivers, you've probably noticed this, that where the river gets really, really narrow, it gets really fast. And where the river tends to widen out and the cross-sectional area is bigger, the speed of the fluid tends to go down. So we see this a lot. It's also very important in physiology. So when you have basically fluid moving through any of the vessels, like blood or air through your lungs, you're going to have continuity become an issue, in that you've got a certain amount of fluid moving from one point in the body to another, and the speed of that fluid is going to depend on the cross-sectional area of whatever passage that fluid is moving through. And that becomes important for considering the impact of the Bernoulli effect. And one rather unpleasant aspect is something called an aneurysm. And that's when you have a weakening of like a blood vessel wall, and the pressure will tend to make that vessel wider right there, sometimes even causing a little bit of a bubble to form. And that increases the cross-sectional area of that vessel. What do you think happens to the speed of the blood right there where you have that widening? Can someone tell me? If the vessel widens, what happens to the speed of the blood right there? Yes, it slows down. If it slows down, what do you think happens to the pressure if the fluid slows down? Who said that? Man, what's your name?
Yadira?
That's right. I just have to find you. Yadira, did it? Okay. Okay. So it gets, if it slows down, well, the pressure increases. Well, what do you think happens to that blood vessel if the pressure increases right there where you've got that weak spot? It's going to inflate a little bit more. It's going to widen. And as that vessel widens even more, the fluid velocity slows even greater. And that increases the pressure again. You see how this might be a problem? This is called an aneurysm. Fortunately, the material that our vessels are made of tends to get stronger if it's stretched, so it resists it a little bit better. But even so, if you've got a weak enough spot, the vessel just might lose. And you could even get this bubble or this wide spot get to be so bad that it could pop. And that could even be fatal if it's in your brain. So not a good thing to happen. Also a contribution, this is rather morbid, contribution to sudden infant death is due to restriction of the airway. So that they tell you not to put your infant face down because there's a greater chance of the airway being somehow restricted. And if the airway of a kid is restricted, especially if they have a weak trachea, and that's fairly common in newborns especially, if it gets restricted, continuity tells us that you're going to have a increase in speed. As if the area becomes restricted, you might have to breathe faster, and you're going to get a faster velocity of the fluid. And so if this happens in your trachea, what's that going to do to the pressure in the trachea? If the air is moving much faster. So if you get a restriction, you're going to have to breathe faster in order to get the same flow of air. Any thoughts on what will happen to the pressure if the speed of the air increases?
A message from Crystal says pressure decreases.
Pressure decreases. And the problem with the trachea is you've got atmospheric pressure around you. And if the pressure inside the trachea, because you're having to breathe very quickly, drops, and if that trachea is weak, the atmospheric pressure could crush the trachea and you can't breathe anymore. And that's one of the contributing factors to what we call sudden infant death. So that was Ms. Scheiss?
Ms. Scheiss.
Okay. So that's a problem. It's also a problem in certain breeds of dogs. There's certain poodle breeds, for example, are bred for a long, thin, graceful neck. As a result, they often have weak tracheas. For this reason, there are several breeds of dogs that are not allowed to breed on their own, not allowed to breed naturally. In fact, many of them are kept on a low dose of sedatives so that they do not get excited. Because if they get excited, their respiration rate could increase, the pressure in their trachea could drop, and the atmospheric pressure could crush their trachea. Why we breed dogs to have this fatal flaw is amazing to me. But we do strange things. Okay. Now, where we, let's see. I think there was something else I wanted to say. Oh, yes. We talked about floating and sinking and density and buoyancy. Well, it's interesting in that as things change from one state of matter to another, well, you get density changes as well. And there's very one fortunate density change, and that's with water. Water, frankly, is weird. It is very strange for the solid phase of any material to be less dense than the liquid phase. But that is the case with water. For that reason, ice floats. As far as states of matter goes, that's a really odd behavior. In almost everything else, the solid phase is more dense than the liquid phase. But because of this quirk, it makes life a lot more possible. Because on this planet, imagine what it would be like if when water froze in lakes or streams or even on the ocean, that the ice would sink. That means in time, our oceans would be frozen solid. In fact, there's a time going back in history when our oceans were mostly frozen. It's called the ice ball Earth phase. Long time ago, not very conducive to life. And so the mere fact that ice floats makes life a lot more possible, makes this planet a lot more amiable to life because ice, in fact, floats. Imagine what the world would be like if ice always sank. Wouldn't be nice. But also, we have some odd density changes with materials. In that, in general, the warmer a material is, you get thermal expansion and something becomes less dense. So the warmer something is, it's lower in density. So, for example, in gases, warm air tends to rise. We'll talk more about that a little bit later this lecture, I hope. And also, when you warm most fluids, they become less dense and they tend to rise. And that's true for water over a large range, but there's actually a maximum density for water, and that's at 4 degrees Celsius. In that, if water is colder than 4 degrees Celsius, it's actually less dense and tends to rise. And water that's warmer than 4 degrees Celsius is less dense also, and it tends to rise. So this is also kind of related to the odd behavior of solid water being less dense than liquid water. But what this means is that in, say, in a mountain lake, where it's really cold outside, the warmest water is going to be at the very bottom of the lake, and it's going to be around 4 degrees, because that's where the maximum density is. And that the colder water will actually tend to be up at the surface of the lake, where it's going to freeze. And so this is why trout can survive in mountain lakes, even in very, very cold winters, because it's always guaranteed to be about 4 degrees at the very bottom of that lake. Does that make sense? So water is kind of odd, but it's not the only material that's odd. Rubber is another odd one, in that most materials, as you get them hot, they expand. Rubber contracts when it gets hot. And that's one of the big reasons, not just because it has a high coefficient of static friction with a lot of materials, it's because it's got a thermal expansion that's actually, its coefficient's negative. So it actually contracts when it gets hot. That's convenient. Imagine going on a long trip in your car and the tires get really, really hot. Wouldn't it be awkward if the rubber expanded? What would that do between the gap between the wheel and the tire if the rubber actually expanded? Would that cause a gap? It might. The hotter rubber gets, it actually contracts. So its seal, its contact with the metal wheel actually becomes stronger and tighter the warmer it is.
I've got a question, Dr. Steve.
Yes.
Does the depth matter for temperature? Like a shallow lake would freeze to the bottom?
Well, if it gets cold enough, it will, but it'll freeze from the top down. That's the important point. It won't freeze from the bottom up, because the bottom of the lake, if the water is, really cold, you're going to have the warmer water that's closer to 4 degrees sink and be at the bottom of the lake, and so that'll be freezing last. So it's not that it's not possible to completely freeze water. It is. You see that in puddles all the time. It'll be completely frozen, no liquid at all. But it will always freeze from the top down, because the more dense water is going to be at the bottom of the puddle, at the bottom of the lake, or the bottom of the stream. So rubber, it's kind of nice that rubber has that odd behavior, because it'd be rather awkward if the rubber had actually expanded more than the steel of your tire, or your wheel. You don't want that. Okay, so that's a few things that I had neglected to bring up that I wanted to when we're talking about both fluid motion and with the thermal expansion stuff. So I'd like to go back and do an example on specific heat. And again, the heat you add to something will result in a temperature change. And the amount of temperature change you get is determined by the mass of the material and the specific heat. That's what C is. And a good question is, if you add 200 joules to 10 grams of water and to 10 grams of lead, what sort of temperature change would you expect to see? And so, solving for delta T, which is divided by mass and specific heat, the temperature change is equal to the heat divided by MC. And for water, well, we got 200 joules, 0.01 kilograms, which is 10 grams. And for water, the specific heat is 4,190 joules per kilogram degree Celsius. And again, you always want to keep the units around to make sure. So our joules are going to cancel. Kilograms are going to cancel, because we've got kilograms here and then 1 over kilograms over here. and we're left with basically 1/1 degrees Celsius, which gives us units of degrees Celsius. So our units check out. If I had degrees of inverse Celsius, that tells me I made perhaps a division error, but I didn't. But if you put in the numbers, we get about 5 degrees. So add 200 joules to 10 grams of water. That's like, a nice size serving of scotch. You're going to get a degree, about a 5-degree temperature change with those 200 joules. If we do the same thing to lead, we'll have 200 joules, again divided by 10 grams, but the specific heat is 128 joules per kilogram degrees Celsius for lead. So we'll get a temperature change of 156 degrees, which could start to be problematic because the melting point of lead is on the order of 300 and some degrees Celsius. So as long as we're talking about room temperature lead, we'll still be fine, but we'll get very, very warm lead. Lead's so hot it'd burn you if you touched it. So don't do that. But it wouldn't be molten lead. But it's amazing how much of a temperature change you get for adding the same amount of heat to water and to lead. And this is one striking thing about water. It has a huge specific heat. It takes a huge amount of energy to change its temperature. That's another thing about water. It's really weird. But that's actually kind of convenient. I was able to get a lot more tomatoes this year in my garden because we had a couple of hard freezes, at least where I live, which is not quite, it's on the hills outside of town. And to prevent the tomatoes and my squash and my melons from freezing, I put water in milk jugs and stuck them around on the ground, around underneath the tomatoes and around the melons and the squash, and then covered the whole things in blankets. So you've got a blanket covering the plant and several liters, about 10 liters in various jugs and containers around each plant. Because it takes a lot of energy to change the temperature of water. And that helps protect plants when you do this. So we had tomatoes a little bit longer with this very nice warm weather we've been having here, even up through the beginning of October. And this is also why you tend to have some of the weather patterns we see. The Pacific Northwest, where we get the weather coming in off the ocean, is a lot more temperate than you might imagine for our latitude. In that, because you've got a lot of water right there, and you see this around islands too, you don't get that much variation in temperature because the water, it takes a huge amount of energy to change its temperature. And so you tend not to get the temperature extremes as a result when you have a lot of water. And this also drives currents throughout the oceans as well as in our atmosphere. So it's a very, very important effect, this specific heat of water. So if you live near a large lake, you might notice not as big a temperature change. If you do a lot of hiking and camping in the mountains, if you're camped near a lake, you won't nearly see the extremes in temperature than if you, say, camped up near a ridgeline. So another example of the importance of specific heat. So I'd like to get into the methods of heat transfer. We've kind of danced around a little bit, but there are three primary methods for the transfer of heat. We have conduction, convection, and radiation. And remember, heat is kinetic energy on the molecular scale. And it's essentially related to vibrations. And you can think of, if you get a really hot region of a material, the molecules there are going to vibrate more, and that's going to vibrate the rest of the material. And especially if the structure is fairly rigid, like what we get with a lot of metals, where we have the atoms actually forming kind of a metal lattice. We talked about, simple cubic, body-centered cubic, face-centered cubic sort of structures of the atoms in a solid. You get that a lot in metals. And because of that, metal tends to conduct heat very, very well. Not only do you have electrons that are free to move over long distances, so most metals, in fact, conduct electricity. They're very efficient at transferring energy from one part of the material to another by these thermal vibrations. Again, these are vibrations on the molecular scale. So metals tend to be very good conductors of heat. And remember, the metal plate that we passed around in class yesterday, and hopefully those of you at home tried this out as well. Metal will feel cool to the touch because the rate at which it transfers heat away from your hand is quite high, much higher than you'll have for most anything else you can touch. Water at room temperature will feel cold to us, even though it's the same temperature as the air around us, because it conducts heat better away from us. And it also takes a huge amount of energy to raise its temperature. And different materials have different thermal conductivities. So, did you have the tank for this?
Grab the new one.
So we have here is we have 4 different chunks of metal. We've got a copper rod coming out over here. We've got a brass rod coming out over here. We have aluminum coming out over here. And we have a steel rod coming out over here. So, what do you think conducts heat the best of these metals? Aluminum, copper, brass, or steel? And those of you who are at home and have access to Google, maybe Google thermal conductivity, and can someone tell me which of these metals has the highest thermal conductivity? It's also going to be the metal that has the best electrical conductivity, because the two tend to go hand in hand. And you better give me an answer before we actually do this demonstration.
So Raiden has an answer.
What's the answer?
Copper.
Copper. Okay, what's next after copper? Okay, in fact, I'll let you do this. You go ahead and light that and then hold it up there. And we're going to watch to see which candles fall off the first and which candles fall off the last, because they're melted on here. And as the rod gets hotter along its length, we're going to see the wax melt. And so whatever rod has the lowest thermal conductivity should have candles clinging for the longest time. And the ones that have the highest thermal conductivity, the candle should be dropping off first.
So Crystal is saying that it goes from the least dense to the most dense?
Not density, thermal conductivity is what we're looking for. And copper does, of all these metals, has the highest thermal conduction. This also has the highest electrical conduction. So my question is, which one has the least? Who is it that said copper?
It was Raiden Hunter.
Okay. So let's just watch this for a little bit. Oh, that was on aluminum. Our first candle fell off on aluminum. Then we had one coming off on copper, 2 off on aluminum, 1 off on brass, 2 off on 3 off on copper. Oh, it looks like aluminum won, and it looks like copper's coming in second. And brass? This is going to take a little while, apparently. It looks like brass is going to have a higher thermal conductivity than steel. So it looks like steel has the, we could probably stop. So we had what looked like almost a tie between aluminum and copper, but aluminum melted off first. And I thought that copper had the higher thermal conductivity. In fact, I'm pretty sure it does. So, but we have some slight variations then by how much wax was holding it on. Might have been a bit different, but it was pretty close. But the big difference where steel had the lowest thermal conductivity because it still has candles on it. And then we had brass. So looking at the thermal conductivity, if you look at this, copper has the highest, followed closely by aluminum, and then brass and steel is last. And that's kind of what we saw here, except that the aluminum actually melted sooner than I had expected. Okay, convection is a form of heat transfer that's a little bit hard to comprehend, in that conduction is basically from vibrations in the material. It's almost like electrical conduction. With convection, it's basically mass transfer. It's basically the physical motion of mass from one place to another. And we've got a demonstration over here in this box. Brady, go ahead and get that going. So we've got basically a candle down here in the box. And we have some chimneys. We're going to want to have that so that you can see it with the.
Yeah, why don't you?
Probably just pick it up if you could. So what we have is kind of a chimney box, in that this is sort of like what you see going on in a chimney, in that we've got a candle underneath this chimney over here. And again, hot air rises. The candle heats the air. You will tend to rise up this chimney, and that will create a draw. You'll actually start pulling air down this chimney as the air leaves and rises here. So we should get kind of convection going. And if we put the incense over here, look at that. It's like almost something's blowing it from underneath. Can you see that? So move it away from the chimney. Yeah, compared to right there, we have just that kind of smoke billowing, slowly rising, but right above the chimney, it's like it's being blown from underneath. Can you see that in the back of the room? Okay, now if we put it over the other chimney, look, it's being sucked down. Some of it's still rising, but quite a bit of the smoke is being pulled down that chimney and circulating, and will actually start coming up here. It's sometimes kind of hard to see unless you're close, but eventually we'll get some smoke coming out over here, but it's kind of diffuse. But you can clearly see it being drawn down that chimney, where over here it was being pushed up. This is convection. You typically get this when you have one part of the fluid that's warm and another part that's cool. You're going to have motion of the fluid from the cold part to the warm part. And this is also why if you have vents, they're often placed, near windows or near a wall to try to get convection currents to circulate the air throughout your room. As the warm air rises out the vent, it'll rise to the ceiling and it will tend to fall, especially near a window. And you also see this in the ocean. A lot of the ocean currents are driven by these temperature differences. And that circulates material throughout the ocean and also circulates nutrients for things to feed on. And you get these currents right near continental shelves where nutrient-rich water at the bottom is then warmed and then rises. And that's where a lot of fishies and things like to feed. So pretty important for a lot of, they're probably good with that.
I don't remember how that's.
Oh. You could also do it with your fingers, but that hurts. Okay, we've got another demonstration of this. We've got some water that's being heated, hopefully boiled, and it's dyed red, and we're going to inject it down low in this long, narrow trough. And Braden's putting in some ice up here on one side. So we're going to get one side that's going to be kind of cold. And if we put some warm red dye down over here, dye that's going to be warmer than the water around it, we should expect that that warm water should rise. And once it gets to where the water is cooler, well, it should then fall. So we're going to hopefully see a convection current form here. That's probably warm enough.
Use the dolly.
Braden, you know where the eraser is? Not on the tray.
Yeah, there's the magnet one there.
Ah, I see it. He was hiding from me. So we injected this at the bottom. You can see it rises. It clearly rises. And as it moves and diffuses over to where the water is cold, well, that's going to cool the water where the dye is, and it should start to drop near the bottom of the tank. And yep, we're seeing that red dye go down. And as we put more warm water over here at the end, we might actually get a convection current going. So as that warm water rises, that's going to pull water off from your left more over to the right. And you can see that kind of warm water moving over. And the dye is starting to fall again. It might be a bit long to see that convection current, and you need to basically have a continuous source of heat. If we had basically had something that could continually warm the water over there on the right side, you would see this. But you could clearly see the dye rising because it's warm and then falling where it's cool. And it looks like we do have dye starting to move back to the right. Okay, so that's a decent demonstration. And the last form of heat transfer is radiation. In that basically we are luminous critters. A lot of the light we emit is in the infrared that we can't see. But pretty much anything at any given temperature emits light. The warmer an object, the more energy it radiates as light, or what we call heat. It's basically heat transferred through basically electromagnetic radiation or light. We call it infrared radiation. And so literally we're glowing if you look at very, very low frequencies. And pretty much everything around us is constantly emitting light based on its temperature. We tend to be warmer than our surroundings, so we are basically radiating light more so than our surroundings. We're also absorbing heat from our environment through this radiation. And you can certainly feel it if you go out in the sun. You can feel the warm sunlight on your face because that's basically radiation you're feeling. It's heat being transferred in the form of light. And we can also lose that energy by radiation. One of my colleagues, Dr. Soul, down at Utah State University, he's at Weber State University. He works at Search and Rescue. He's a volunteer for Search and Rescue, does a lot of especially winter and alpine rescues. And he has told some rather interesting stories over the years. And the number of times when he's gone after a party of hikers where people have gotten so cold that their survival is at risk. He says, he has said that it's like a universal. The people with hats tend to live and the people without hats tend to die. That's because since we have quite a bit of blood flow to our heads, that's where we tend to radiate a lot of our heat. And having some sort of covering on our head limits the radiation that we lose. And people tend to lose heat more rapidly on their head. So if you're outside And in some sort of situation like that where you could have to spend overnight or maybe experience bad weather, especially in the winter, head covering is critically important because that could be a big killer. Also, he's told me that when people are right on the edge of survival and they're trying to evacuate them out, sometimes on horseback, sometimes on stretchers, that the worst thing that they could encounter is a clear sky. Because if there's clouds, that tends to trap in this thermal radiation that's emitted by the ground. And you also tend to have the clouds emitting thermal radiation. But if you have a clear sky, there's nothing to reflect that thermal radiation back, this light, this radiation. And radiation will just, from everything, will just escape out into space. And that's why clear nights tend to be far colder than nights where you have clouds. And the worst thing they can see when trying to get somebody out in an emergency situation like that is to have the sky clear, because that's going to drop the temperature, and somebody right on the edge of survival, that could be a telling point. But you probably noticed when things get really, really hot, you could actually start to see them glow. In fact, we talk about, red hot and white hot. And anybody who has horses, I'm sure you've either been involved in horseshoeing or seen a horseshoer work where they've got the forge and they're heating up the horseshoes. The metal will start to glow a dull red, and when it gets really, really hot, it will look more yellow and even start to look white and even develop a little bit of a bluish tint to it if it's extremely hot. And that's because the frequency of light that's emitted from an object increases with its temperature. So you can even do a graph. The Hewitt has a graph like this. We tend to have curves with a clear peak in frequency and so we'll get more intense radiation on something warmer, and the frequency of its peak will also shift to higher frequencies. And typically, visible light is out over here. And so we tend not to see the thermal energy that things emit. But if you get something hot enough, you can see this. And the models we have for this actually match things pretty well. But most objects, this intensity curve is rather complicated because not only do you have the light that's emitted by the object due to its temperature, you also have light that's reflected off of that object, and that tends to complicate things. The simplest object to describe is one that doesn't reflect any light at all. Those are called black bodies. And so if something absorbs all of the incident light, and so what it emits is only due to its temperature, it'll have very nice bell-shaped curves like this. Other objects will be more complicated because you have reflected light coming into play as well. And so we call them black if they don't reflect any light. And I actually have a black body here. I kind of regret that the student that built this for me actually painted it black, because the black bit is the hole. By having this big box with a hole, it's not the box that's a black body, it's this hole. And that if we were to look at the light that comes out of that hole, it would have a very predictable spectrum, this intensity curve. It would be like that of a black body, because the light that enters that hole is pretty much, it's going to bounce around inside this box and is eventually going to be absorbed. so that the amount of reflected light coming out of this hole is like negligible. Pretty much all the light coming out of that hole is solely due to the temperature of the inside of this box and the colors of light that are emitted by any material due to its temperature. So that's what's meant by a black body, not the box, but the hole. Does that hole look black? Pretty much it looks pretty dark. But the inside of the box is actually quite bright. So this is the hole is the black body, but the inside is quite reflective. And we've got felt lining to pretty much keep any light from entering, and the sides and the seams are pretty well sealed. So this is very much a black body for that reason. I've got another, basically, you can also have something behave like a black body if the amount of its reflected light is negligible compared to what it's emitting. And you tend to get that when things get very hot. So when you get something very hot, yeah, it's also reflecting light, but the intensity is so great that you're not going to notice it. And that's what I have here. And I would like everybody in the classroom to come down and grab one of these diffraction gratings. Basically, these are like prism glasses. They break light up into different spectra. We'll talk about light spectra later, but you want to keep kind of a social distance. So I want you to come close as you can, but still keep 6 feet different distance. So somebody can like go over here, somebody over here. Try to get as close to this thing as you can while still keeping about a 2 meter or 6 foot separation from each other. And we'll want all the doors closed. And I'll get these lights first. So let me get this on. Before, I've got this set up to a variable transform. Oh, Braden, we needed a clear bulb. We can't have a frosted bulb. You have to have a clear bulb for this demo. Sorry. So you want to be looking at the filament. Okay, so you want to look at this filament. And these incandescent light bulbs work because you send electricity through a very, very thin piece of tungsten that gets very, very hot. We'll talk about that when we get to electricity. And because it gets very hot, it emits light. And so if I have it barely on, it kind of looks reddish. And if I turn it way up, it looks like a bright white light. So what I'd like you to do, let's go ahead and turn off the lights, put on the glasses. Oh, we need to pull out the candle. Could you blow out the candle, Braden, please? Okay. We put, this is not going to show up well for people at home, unfortunately. Could we have it so we don't get the lights coming off those screens at all, Colton?
Here, I got it.
You got it?
Okay, so I've got this down at kind of a dull red color. And when you look at this, you should be, can everybody see this filament? If you look straight at the filament.
Yeah.
Okay, I'm going to increase the current and increase the temperature. So do you see something in your glasses besides the red color? Are you starting to see maybe some yellowish bands? As I increase it still further, you should see definitely some more yellows, maybe some oranges. And if I make it even warmer, you should start seeing less red, but more of the yellow color. Well, the red should still be the dominant one. As I make it brighter and brighter and brighter, it looks like the mean color shifts from red to more orange and yellow. Does that match what you're seeing?
Yeah.
And I don't know if you can have that, like a diffraction grating over the camera lens or not.
Kind of wondering that. Can you grab one, Greg?
Yeah.
Works better than I thought.
Can you see a spectrum?
Yeah.
Okay, now let's go the other way. This is as hot as I can make it. And as I turn the dial down and get cooler and cooler filament, the red should start to increase as far as its relative fraction. And you should start losing the greens first. And then start to see a decrease in the yellows and then the oranges. Is that showing up okay on the screen?
It's staying pretty constant for all the colors.
Okay, well, I haven't got to really cool yet.
Yeah, that's working there.
It's actually showing up on the camera,
Yeah, surprisingly well.
okay?
And
Is it still visible?
just barely.
Okay, we still have a long ways to go, so this is not the best with the camera.
Oh, now we're also getting spectra from the LED.
Yeah, I bet you are. Okay, that's good. Let's get the lights back on. And gosh, I had some slides I wanted to go through. Let's go ahead and pull up the first slide.
Okay, the printer comes off.
And at least we'll talk about it. We might not be able to resolve this until tomorrow, but at least let's get the question out there.
Do you want us to do these?
I just put them back with the stacks of those. Actually, I think I'll just do some Blackboard stuff. We really don't have enough time for a concept test. So let's switch back to the camera. So okay, what if you turn off the screen over the projector over here?
Got that, Greg?
Put down some stats. Just to kind of put things in perspective, if we're talking about room temperature air at 1 atmosphere, the mean free path of molecules. I remember I mentioned the kinetic theory of gases, where the air around us is made up of molecules are constantly moving around and colliding things and hitting things. And it's their impacts that give us pressure. At room temperature, how far do you think an air molecule has to move before it actually collides with another air molecule on average? Any ideas? Kind of an order of magnitude? Something you don't have much of a comprehension for? Maybe do a thing with your fingers. Any chat comments? Nope. Oh well. It's about 70 nanometers, which is a teeny fraction of a millimeter. Thinner than your human, than your hairs. We're talking about really extremely short distances before an air molecule collides with another molecule. And we have about 7 times 10 to the 17 molecules per cubic centimeter. So basically, in a volume of air about the size of the end of your thumb, you've got almost 10 to the 18th molecules. And that means the average separation of air molecules at room temperature is about 10 nanometers. So shorter than the mean free path, which makes sense. So yeah, air is very low in density, but there's still a whole lot of air molecules in a cubic centimeter and not very much space between molecules, and they certainly don't go very far before they collide with another molecule. Compare that with something in a solid, where the average separation of the atoms in a solid, like a metal, is on the order of 1/10 of a nanometer. So we're talking about several orders of magnitude difference in density, like factors of millions in density between a metal and gas. So the average separation inside a metal of the atoms is on the order of, well, an angstrom, which is about 10 to the minus 10 meters, or about 1/10 of a nanometer. And we'll talk more about what this actually means